speaking to you today. So I'm Jamie. I'm a mobile architect at Embrace. So I work on Embrace's SDKs that would be on Android, iOS, Unity, and React Native. And I've always had a particular love for Android development. I've been doing it probably since the days of Donut. And yeah, I'm really excited to share with you what we found out about ANRs. So why are we here? It's because of this line. So effectively, you need to stay below this orange line, which Google have set in order for your app to still get organic acquisition on Google Play. So this is a threshold of 0.47% of your sessions are allowed to have ANRs. And if you go above that, then there's some consequences to that. So you get a lower Play Store ranking, so you don't show up as much in search results. There's negative reviews, which also impact your business. And it's just generally a poor user experience when an ANR happens. And some of those consequences to your business's revenue are fewer purchases, whether that's in-app purchases or checkout in an e-commerce app. The users that you do have are less engaged with your app because it's a frustrating experience. And there's just generally less installs and a poor perception of your brand, which hurts your business. So there's two real reasons why we find that mobile engineers struggle with solving ANRs, and it is a really hard problem to solve. So the first one is the data that you are given by Google, Firebase, and other providers doesn't really show you the whole picture of what's going on. And the second thing is that some engineers do have a limited understanding of what an ANR actually is. It's quite commonplace to think that if the main thread is blocked for 5 seconds, then that's an ANR. But we've had a look at the documentation and the Android source code, and there seems to be a real disparity there. There's actually quite a few conditions where an ANR can trigger, which we'll get to later in the webinar. And the spoiler is, it's not always 5 seconds. So let's briefly just run over the agenda for what we're doing, for what we're going to be talking about today. So firstly, we're going to cover what the current ANR data looks like and what its limitations are. Then we're going to go over what the different ways are that you can access this ANR data. Then we're going to dive into how the Android OS itself triggers ANRs. So that would be how the 4 components of Android, that is an activity, service, content provider, and a broadcast receiver, trigger ANRs and what those thresholds are. Then we're going to talk about once an ANR has been triggered, how does the Android framework actually collect data, which is sent to common solutions. And then finally, we're going to touch upon what Embrace's solution is for solving ANRs. So firstly, let's cover the current ANR data and some of its limitations. We'll firstly just reiterate what the difference is between an ANR and between a crash. So a crash, I think most people will be fairly familiar with and will have experienced it either as an end user or as an engineer. It's a coding error that's immediately going to kill your application. So for example, in an e-commerce app, your user might go to the checkout screen. If there's some sort of bug in the checkout code that causes a crash due to an uncaught exception or some C signal, then the app will crash, and you'll usually be given a stack trace, which can be fairly easy to address the issue from. Contrast that with an ANR. If a user goes to a checkout and they experience an ANR, then the screen will just not respond for them. And there's multiple reasons why this could happen, and it's really hard to diagnose. You could have just a heavy UI layout, which blocks the main thread for slightly too long. You could have a third-party SDK which is misbehaving. You could have background services which are blocking the main thread because you need to synchronize until you get a result from that service. And these all lead to the same poor experience. So one problem with the data which you currently get is that you're effectively given a stack trace. And this is because the Android operating system treats an ANR as if it was a crash. So take this diagram, for example. If your app is running normally and then suddenly starts freezing, the user can't interact with it. And then at some point later on, say about 5 seconds or so, Google or the Android operating system captures a stack trace of what's happening at that time. The app can then be either terminated or the user can choose to wait. A dialog will be shown to them. And really, this is a problem because you just get given the picture at the very end. So if you watch South Park, this image sort of sums it up. Android's approach is in phase 1, ANRs are basically not crashes, but Android provides the data as if they were crashes. You just get a single stack trace towards the end of the ANR when often you want to know the whole picture of what was happening. And phase 3, that's where you are. You find it very hard to actually go and solve the issue just from a single stack trace. So next, let's just cover some different ways to access the ANR data. And if you do have any questions about any of the previous section, please feel free to put them in chat, because I'm aware that this is a lot of information. So basically, the Android framework monitors from the background thread the main thread to make sure that it is still capable of doing work. So in our example here, the Android OS is monitoring the main thread from a background thread. And once it detects that the main thread is blocked or performing some sort of work, it's going to start an ANR timer on that background thread. And if a particular time threshold is exceeded, let's just say 5 seconds for simplicity, then at that point, the Android OS will trigger an ANR. So there's a few pieces of information which you can access in development, which allow you to debug ANRs. So after the Android OS has triggered an ANR, it will record various pieces of information. So you'll get stack trace for main thread and some other threads. You can also get information about other processes in case the system is overloaded by dozens of apps doing work at the same time. And you can get various other bits of metadata like CPU information, memory information. And this is sort of the best case if you can get this information in a development device. Quite often, in our experience, it's been very hard to reproduce an ANR in a development environment, and you aren't able to get this information. So there's a couple of other solutions which are fairly widely used for getting information about ANRs in production. Two main tools, really. So there's Google Play Console, which is available to anyone, and Firebase Crashlytics. So let's just dive into how they collect data on ANRs. We'll start with Firebase Crashlytics. So they use an API which was added in Android 11, which effectively records the exit reason for a process. So effectively, they read this via an application exit info API, which is recorded on the device each time an ANR happens. And that data is collected from Firebase when the user relaunches the app after an ANR. This is in contrast to Google Play Console. So Google Play Console actually use the Android OS's built-in trace file mechanism, which is recorded on the device's file system. And the advantage of that over Firebase is that it's supported on all Android versions, but I'm sure many of you will be familiar with the delays in that data and the fact that the stack trace isn't always that useful in terms of grouping. There's a couple of other options which are out there for collecting ANR data, which I'll just touch upon. So you could basically take a DIY approach of doing it yourself. You could use a watchdog thread, which is just some background thread which checks whether the main thread is performing work quickly enough. And if it's not, you can capture one stack trace at the end of that. There's other third-party monitoring solutions which take the same approach. And there's a couple of solutions which do more hacky behavior, like catching SIGWIT in a signal handler, which kind of works, but it's just the same as using a watchdog thread to get that last stack trace. So I alluded to this a little bit in the last slide, but one of the problems we find with these approaches is that you're just getting the symptoms and not the underlying root cause. If your app freezes, you want data about what's happening immediately when it freezes and during a freeze, and you don't want to know what happened 5 seconds afterwards because your app will typically have moved on. So let's go through how the ANRs are actually triggered by the Android operating system. So we dove into the Android source code and found out that the reality is a lot more nuanced than the documentation says. I'm sure that many of you who are Android engineers will probably have heard that if the main thread is blocked for 5 seconds, then it will cause an ANR. And that is somewhat true. It's true for an activity where if you block the main thread for 5 seconds and the input dispatch queue has pending events, then that will trigger an ANR. There's also a few other cases. For example, if your service is blocked for 10, 20, or 200 seconds, then that can also trigger ANRs. And broadcast receivers and content providers have their own particular thresholds. And we'll dig into these in a lot more detail in the next couple of slides. So basically, I'd just like to go back to how the Android OS monitors whether an ANR is occurring. So an ANR is fundamentally when the main thread is performing too much work or it is blocked for a period of time which is excessive and is going to degrade the user's experience. So the Android framework has a background thread which checks whether the main thread has completed work within a certain amount of time. It has separate checks for each component. So there's one check for an activity, one check for a broadcast receiver, and one check for a service and content provider. And if that time threshold is exceeded, effectively the Android OS itself is going to trigger an ANR by calling ANR helper app not responding. So we'll just go into what the thresholds are for an activity to trigger an ANR. So a brief recap, I'm sure most of you will be familiar with this, but an activity is just a component which shows some sort of user interface. And there are a few conditions where an ANR can occur for an activity. So basically, if input dispatching takes more than 5 seconds, that is going to result in an ANR. And what does an input dispatch really mean, though? So if you tap on the screen of your device or if you enter something onto the keyboard, the Android operating system interprets that as an input event. So these are put on a queue and this queue can only be processed on the main thread. And if you think about it, the Android OS really needs to process this quite quickly, because if you click something on your device and it takes more than 5 seconds, then it's going to feel like a really slow experience and it won't be fun for the user. So Android does this by using a watchdog thread, which checks whether the main thread is still processing any input events. And if it's been more than 5 seconds and it's still processing input events, an ANR will be triggered. We'll just run through this quickly with 2 examples. And an interesting point here is that you need to actually trigger some sort of input event to create an ANR. So in this example, we don't have an ANR. The Android operating system is still monitoring the main thread from the background thread, and the main thread is blocked, but there isn't any user input event, so nothing happens. And this kind of makes sense. Effectively, the user didn't see anything, so nothing bad happened and we don't need to show a dialog. In contrast, if the main thread becomes blocked and the user clicks a button, for example, shortly afterwards, then that is when the ANR timer is effectively going to start from the operating system perspective. And if the main thread remains blocked for 5 seconds, that is going to trigger an ANR within the activity. We have a diagram here which just summarizes that sort of logic flow of how the Android OS triggers an ANR. So firstly, we start off with the Android framework, which is going to schedule some work in your activity component. So it may need to respond to a lifecycle callback, or it might need to render something on the screen. Then your user is going to create some sort of input, either by tapping the screen or entering the keyboard. That gets relayed to the input dispatcher, which basically puts the event on a queue. Now, if that queue takes longer than 5 seconds to process, it indicates that your app is doing far too much work on the main thread and something's blocking it. So the Android framework from its monitor thread will then call in to ANR helper, as we discussed before, and that will basically indicate that the ANR threshold has been exceeded. Once that's happened, the Android OS will record a trace file, which will contain information like the stack trace, which we saw previously. And ultimately, once it's finished that, it will show an ANR dialog. At this point, your user can decide to kill your app, in which case the process is terminated, or they can allow your app to continue waiting and see if it catches up. Next, we'll cover what a service ANR thresholds are. So just to recap, a service is a component in Android which typically performs long-running operations in the background. So stereotypical examples of that might be a service which tracks location or performs some sort of consistency check on the database at regular intervals. And there's 2 places where an ANR can trigger in a service specifically. So that is if a foreground service does not call start foreground in under 10 seconds, then Android will trigger an ANR. And a foreground service, just to recap, is something which typically is going to be performing work in the foreground. So for example, music playback. The other condition is if the service doesn't start or bind in under 20 seconds. Or if the process itself is in the background, that is to say, maybe your app was opened a couple of hours ago and doesn't have the highest priority on the CPU, then this threshold gets raised to 200 seconds to allow you a little bit more time. And we apologize for terminology here, it's quite confusing, but that is how Android has named it. So this diagram just recaps the logic flow of thresholds for ANRs. So first off, the Android framework is going to schedule some work in your service. It might create a service in response to some system broadcast or just your app launching. If your app is a regular service, then Android is going to check if your process is in the foreground or not, because that indicates that it's got some sort of importance from, and will have more CPU time scheduled. So if your process is in the foreground, you have 20 seconds to start or bind your service. If not, it's 200, so it's a bit more lenient. And with a foreground service, you have 10 seconds to call stop foreground. And if any of those thresholds are succeeded for a service, then a trace file will be recorded, dialog will be shown, and the users will see a dialog asking them whether they'd like to kill your app. So we'll move on to the broadcast receiver component now. Just to recap, this is something which can respond to system events. So for example, if you are a messaging app, you can hook into an SMS event and perform some functionality in your application. Now, the condition for an ANR and a broadcast receiver is if you take longer than 10 seconds to process a message in on receive, then that will trigger an ANR originating from the broadcast receiver. There's a couple of interesting exemptions to this, mostly to do with when the Android operating system itself is booting. And we think that the reasoning behind this is that effectively the Android OS will be performing lots of CPU work when they're starting up. So it doesn't make sense so much to trigger ANRs for those early broadcasts because they could be false positives. And this diagram just summarizes, again, the same logic for the broadcast receiver. So the Android framework is going to schedule work in your broadcast receiver due to some sort of broadcast. Then if you take longer than 10 seconds in on receive, the threshold will be exceeded. And once the threshold is exceeded, you probably know the drill by now. A trace file is recorded to the local file system, and a dialog is shown to the user asking them whether they want to kill your app. I'll just briefly touch on the content provider. So this is a component which basically provides content to various other applications on the device. So for instance, the Android OS has a built-in content provider which you can access phone contacts with. And there's really only one condition for an ANR to trigger within a content provider, and it's got a really concrete action which you can go away and fix actually. So if you call getProvider MIME type and it doesn't respond in 1000 milliseconds, then that will trigger an ANR in your content provider. And the really easy fix is to avoid using the deprecated getProvider MIME type function. You can call getProvider MIME type async, and that will run in a background thread, which avoids an ANR. And again, this just sums up the state flow for how the OS triggers ANRs. So the framework will schedule some work in a content provider. If you take longer than 1 second in getProvider MIME type, the threshold will be exceeded, and the trace file will be recorded to your local file system, and the ANR dialog will be shown. So one thing which is really important, in my opinion, is that all these components typically run on the main thread, and they're often running at the same time. So we all know that an activity runs on the main thread. If a broadcast receiver and a service are also running at the same time, that can sometimes mask the culprit of who's responsible for an ANR. So in our diagram down at the bottom, we have an example which tries to illustrate this. So you may have a broadcast receiver which takes about 6 seconds to complete, which is quite a long time to block the main thread for. So that won't trigger an ANR in itself. We learned that BroadcastReceiver has a threshold of 10 seconds in which it triggers an ANR. However, if there is a user input event at 1.5 seconds, then we have hit the condition for an ANR to occur in the activity component, because that has a threshold of 5 seconds. So if our broadcast receiver takes approximately 4.5 seconds of blocking the main thread, and then our activity does something which takes a little while but isn't unreasonable, then our activity might be wrongly pointed at as the culprit with Google's ANR stack trace. So that's just an interesting thing to bear in mind, that the final stack trace is not always the full picture, and that it really helps to be able to see what's going on for the duration of the ANR. We have a few other additional thoughts on triggering ANRs and a few practices to avoid them, some of which you may be familiar with. So best practices to avoid ANRs, obviously you'd really want to minimize network operations on the main thread. They can take a long time to complete. Same goes for file operations. You want to offload them wherever possible to the background thread and asynchronously wait on the results. And another thing which is a little harder to do depending on how you use concurrency and synchronization in your app is to minimize the amount of waiting you do on locks and mutexes. So you just want to confine that to the smallest space possible. Another thing we find typically trips people up is NDK code. If you have code in C or C++ that performs file operations, it can be a little easier to forget that that's actually writing to disk, reading from disk, and tools don't usually show that up as well. So we'll move on to how the Android framework itself actually collects data or an ANR stack trace. But I appreciate that was a lot of content, so if you do have questions, feel free to put them in chat. So this diagram sort of summarizes how an ANR trace file is captured by the Android operating system, and also shows how the dialog is shown. So we've sort of gone over how the thresholds are triggered for the different components, and those thresholds all call into the ANR helper app not responding. At this point, some information is recorded into an ANR trace file, which is on the local file system. And the process record error state is also updated. So this is just a representation of, on the Android OS, of whether your process is crashing or having an ANR. And once that's happened, an ANR dialog will effectively be shown to the user. And the user either chooses to kill the app, which terminates your process, or they wait for the app to respond, and the process survives to live another day. There's a couple of reasons why an ANR could be discounted within that dialog, which I've just shown. So they can be discarded at multiple points. So if you have a debugger attached, ANRs get discarded. This is because you could have a breakpoint on the main thread, and it'd be really annoying to get an ANR every time you were debugging. And there's a couple of other reasons. So an ANR might already be in progress. You don't want to show up duplicate dialogues effectively to the user. Or the component or process might be dying or in the process of exiting. And in that case, it doesn't really make sense to show a dialogue either. So I'd like to go over Embrace's solution now to solving ANRs, which I hope you'll see is quite different to Firebase and Google Play Console. So firstly, I'd just like to introduce Embrace. We're a very mobile-centric observability and data analytics company, and we help you drive business decisions through that data. One of our key differentiators is that we collect 100% of data from 100% of user sessions. So you can go on the dashboard, on Embrace's dashboard, and see exactly what a user was doing in the lead up to a crash. We track various metrics like releases, regions, and devices according to the segments you actually care about. And we also provide proactive alerting so that you can get notified pretty much instantly, and that really helps reduce the resolution of issues. So I'd like to also highlight that we capture the whole session, and this really helps with ANRs, we feel. So you get the full context of exactly what was happening in the lead up to an ANR, what the user was doing, what they were clicking on. Whereas with typical event-based monitoring, you do get the stat trace, which can be useful, but you only get that and you don't get any of the context on what the user had been doing previously. And typically, a lot of these solutions haven't been built for mobile, whereas we are built exclusively for mobile. So I'd like to walk you through Embrace's solution for ANRs. So we've taken an approach of distributed ANR sampling. So effectively, throughout the duration of an ANR, we will sample the main thread and gather a stack trace. So you can see here that as soon as an ANR starts, or within 1 second of a main thread being blocked, we start sampling the stack trace at regular intervals. And that allows you to see how an ANR has evolved over time. So how does this work? Well, for starters, you get data a lot earlier than Google. And effectively, we then stitched together similar sessions where a similar ANR happened. And we put this into something which is called a flame graph, which highlights the important methods to look at. So if you've not seen a flame graph before, I won't worry too much. We'll walk through it in our demo shortly. But effectively, the size of each method shows how frequently it showed up in an ANR sample. So larger methods are more likely to be blocking your application's main thread, and that gives you an indication of where the low-hanging fruit are. So there may be some third-party ad SDK or just a bug in your own code that you need to go fix. So we think this approach is better because it gives you earlier detection of when an ANR or freeze is happening. You get the full sort of context of how of what was happening in the lead up to an ANR, and you get multiple stack traces throughout an ANR, whereas with other tools you only get that one stack trace. And we also feel the grouping is more actionable than just getting a final stack trace, and we'll show you why in our demo. So I guess it's almost reframing the way of thinking about ANRs. It becomes not how many times did an ANR occur in my app, it's more how many times was a main thread blocked for an unacceptable amount of time, and what was the main cause so I can go fix it. So I will now give you a brief demo of ANR flame graphs on Embrace's dashboard. So this is the main view you can see when you come onto Embrace's dashboard and select for ANRs. So I'll just run through this briefly because it may look a little different to other solutions which you've seen. So to start off with, you can see you get metrics on how many of your sessions contained ANRs. So this is a fairly good percentage, and it's below Google's threshold of 0.47%. So we know that this app is healthy and it's still getting organic acquisition through Google. And there's also statistics on how many of your users have never experienced an ANR. One thing which you might find different is there aren't any stack traces down here. So what we do is we group methods in stack traces based on their package. So this basically shows you where in the code an ANR is originating from. So for instance, down here, we can see that the ReactiveX library is causing an ANR in 0.04% of sessions, and it's showing up in 0.06% of stack traces. So if I click into this, and I'll just, this is one I've loaded earlier, I can see a flame graph for the IO ReactiveX package. And this can look a little intimidating, but I can just walk you through it. So these are basically Android OS specific calls, so they can effectively be installed. It's the Android OS scheduling work in your app. The one we really care about is the largest methods in the flame graph. So that indicates that the method has been running for a very long time and is likely to be blocking your main thread. So here we can see that there's something to do with ReactiveX, which is blocking our app. And we can go down and get the entire stack trace and see that there's this method here, which originates from our code. So perhaps I would go away and ask one of my engineers to try and optimize that, find out if there's anything that they could do better. We can also see over here that there's a flame graph which seems to be a recursive call. So I could probably, and that seems to be taking up quite a bit of time. It's showing up in 20% of the samples. So that's something that I could almost definitely say as a bug and ask my engineers to go away and address. So there's a couple of other things I'd just like to draw your attention to. So you can group by the last sample, which is the last stack trace in an ANR, or the first sample, which is the very first stack trace in an ANR. The last sample is roughly equivalent to the stack trace you would get from Google, whereas the first sample is collected at the very start of an ANR. So by default, that would be 1 second into an ANR of the main thread being blocked. I can just show you the difference between those two on this other flame graph. So you can see here that on the first sample, which this is grouped by, the fragment pager adapter is taking up a very large proportion of the flame graph, and that seems to suggest with the layout inflator that this is taking a long time to create some view. So I may want to go optimize my layout as a result of seeing this information. And this is what things look like in the last sample. So this is basically what you get from Google. You can see it's very different. You have a lot of layout passes invoked by the Android operating system. And there's still a little bit of view inflation, but it's nowhere near the same. So you can often get quite misleading results if you're just relying on the last stack trace. So I have a couple of other things which I wanted to just highlight. So you can filter ANRs. So for instance, if you're interested in a particular country or a particular OS version, then you can filter to only see ANRs from that particular country. And you can add various other filters there. Another interesting thing is you can reduce the duration of an ANR. By default, we set that to 5 seconds. but you can reduce it down to 1, and that will also affect what you see in the flame graphs. So I'd like to just sum things up with some key takeaways there. So I think we all know that ANRs can really impact the user experience, but importantly, they can also impact your ranking on the Play Store, which in turn affects your user retention and your business revenue. That can really hurt if you've got a very bad ANR behavior threshold. Existing tools like Google and Firebase tend to treat ANRs in the same way as crashes. You just get a stack trace right towards the end. And sometimes that's helpful, sometimes it's not. Whereas Embrace basically tries to get stack traces throughout the entire ANR, which gives you the full amount of data which you'd need to solve the problem. We went through the Android framework's thresholds for ANRs and various different components. So you can hope that there's one thing you can take away from today, it's that an ANR doesn't mean that the main thread is being blocked for 5 seconds. It's a lot more complicated than that. And finally, I hope we've shown that Embrace tries to take a holistic approach to ANRs. So we capture data earlier and we sample stack traces across various devices, which helps surface common patterns in your ANRs, which you can see via a flame graph. Thank you for listening.